that with saying that it's a pleasure to be able to speak in this distinguished audience from the environment of my own kitchen. So here is I try to share my slides. Is it working?
Yes.
So good. So I decided to give a survey talk on this topic, which was the subject of interest of myself and some of my students, namely strictly positive probability logic. So I will be talking also about results of others, and they will play a significant role, also very recent results. So what is strictly positive modal logic? It turned out that historically the interest towards strictly positive fragments of modal logics emerged independently in two different disciplines. And the first one was the work on description logic and its tractable fragments by various people, starting from the work of Bader, Sophronius Stockermans, Walter Zafaryachev, and many others. This work is still going on. And the second story was developing independently, and it came from provability logic needs. And there are a few names here mentioned as well. The two lines of development, they became aware of each other roughly 10 years ago at one of the advances in logic, in modal logic conferences. And since then, we learned quite a lot about it. What is the reason to study, to be interested in these kind of fragments is the combination of simplicity and efficiency on the one hand side, and sufficient expressivity of these languages on the other. In particular, these fragments, which I call strictly positive, they are both, let's say, contextually and also computationally, they are much simpler than the original modal logics. So typically, modal logics are p-space complete, the standard ones, whereas their strictly positive counterparts are polytime decidable, for example. But also many other things about strictly positive logics are much simpler. On the other hand, as it turns out, this language is sufficient for many purposes, and in particular for the purposes of specifying ontologies, as in ontology languages, as in description logic. So, for example, this medical ontology, SNOW-MED, is basically based on the strictly positive logic itself. And in probability logic, there are many interesting aspects here. In particular, also these applications to ordinal analysis can be stated in terms of only strictly positive fragments of modal logic. So that's roughly the reason for the study. What is strictly positive modal logic? So the usual language of modal logic we can view as the extension of propositional calculus by a family of unary connectives. There may be infinitely many such connectives, which are denoted diamonds here. So we have full propositional logic. Modal logic has several major kinds of interpretations: Kripke semantics or relational semantics, neighborhood semantics, and its particular kind of topological semantics, and algebraic semantics in terms of Boolean algebras with operators. Kripke models are, which I remind here, probably don't need a reminder, but a Kripke model is considered here as a structure, as a relational structure, non-empty set W and a family of binary relations together with an evaluation V, which is considered as a map of model formulas to subsets of W, such that it interprets Boolean connectives as Boolean operations on subsets of the set W, and diamonds are interpreted as pre-images under the corresponding binary relation. So the interpretation of diamond I. A is the set of all nodes X in W such that there is some Y, such that X are I, Y. So that's all pretty standard. Then we again write that the formula A is true at the point at the node X if and only if X belongs to the set V of A, its interpretation. So that's standard Kripke semantics for modal logic. In terms of description logic, we make use, so we interpret each of the relations Ri as a binary predicate on W. And each variable is interpreted, propositional variable P is interpreted as a unary predicate on W, roughly the predicate that X belongs to V of P. And then under this natural translation, every model formula A translates into a predicate logic formula in one free variable X. So that's a well-known translation from modal logic to predicate logic, which allows to consider the former as a kind of fragment of the latter. In description logic, they use their own language for to denote various concepts that we know as logicians from the modal logic and Kripke semantics. So here is the little vocabulary that you may encounter reading that literature. So variables are called now concept names, binary relations are called roles, logical connectors are called concept constructors, and diamond I is usually written in this somewhat misleading way with an existential quantifier. Whereas general model formulas are called concept descriptions, and propositional, what we would call a propositional theory, that is a set of model formulas considered as assumptions from which we derive other model formulas, is called a T-box. So that's a description logic terminology which was developed quite separately from logical language, so by practical people working in practice, by engineers working in practice. So that's how the words they used. And here is how, for example, a little piece of a medical ontology may look like in their notation. It's about an explanation of terminology related to diseases, and for example, each line here states certain facts that we assume to be true by definition, like, so endocardi is a tissue and it is contained in the heart wall, is contained in the heart valve, and so on and so on. Then I explained what is endocarditis, like an inflammation and its location in endocard, and so on and so on. So you see that here, all these statements are in fact translated into modal logic formulas on the one hand side. On the other hand, they are very particular kind of modal logic formulas, what we would later call strictly positive implications. each one has an is a form implication, so this inclusion is nothing but an implication, and the right-hand side looks like a conjunction of certain formulas built from variables and model operators and conjunctions and something like that. So that's simple kind of example of an ontology. Okay, so what is now? Let's go back to logic. So strictly positive model formulas are a subset of model formulas defined by the following grammar. So firstly, the variables are strictly positive, constant top true is strictly positive, and whenever A and B are strictly positive, then conjunction of A and B and diamond A are strictly positive. Of course, this is a very narrow class of formulas. Not much can be expressed by these. However, implications of the form A implies B, where A and B are of the above form, where A and B are strictly positive, is already much more interesting fragment. So we may think about it as having only one implication. It doesn't have nested implications. It has only one external implication. But left-hand side and right-hand side of this implication is must be strictly positive. So that's the fragment we are interested in. Strictly positive fragment of a model logic L is a set of all implications A, B such that A and B are strictly positive, and implication A implies B is provable in L. Strictly positive logics in general are consequence relations on the set of strictly positive model forms. That's two basic definitions. And here is an example of a very basic, of our basic strictly positive logics, which is presented here as a calculus of, if you like, sequence where left-hand side and right-hand side consist of only one form, or a calculus of these strictly positive implications, if you like. The system will be denoted K plus because it happens to be exactly the strictly positive fragment of model logic K, basic model logic K. So it has three groups of axioms and rules. Group one is just these two axioms and essentially the syllogism rule, which are saying that implication is reflexive, truth is the top, and it is also transitive. Group two are axioms and rules for conjunction. These are the usual rules, nothing special happens. And third is the rule which is the only thing which remains from the other axioms and rules of model logic K. So, and that's the system K plus. We may notice immediately that this system K plus is closed under natural rules such as substitution. One can substitute for the variable P any formula C, as well as under a version of under the rule which I call positive replacement. So when A implies B and C is any formula, which is supposed to be strictly positive here, then C of A implies C of B. In classical logic, this is does not always hold, because formula C may be non-positive. So the occurrence of the variable P in the formula C may be negative, and then it would be an incorrect, unsound rule. Rather, in classical logic, we have the rule of replacement of equivalence. But in strictly positive logic, we have this more general, more natural, naturally formulated rule. Okay. How to deal with on this slide, I show just a little bit on to get a feeling for this very weak logic. So it is many facts there are resolved in fact easier than for standard mode logic. So, for example, the derivability problem for the logic K plus that I mentioned before is can be resolved as follows. So, suppose to every strictly positive formula A, we can associate a structure T of A, which I call its canonical tree. So it's essentially the same thing as a parse tree of that formula A viewed as a Kripke model. It can also be viewed as the minimal possible Kripke model satisfying formula A at the root. How to build such a model is very simple. If it's, for example, if A is just a variable, it will be just a one-point model with in which this variable is supposed to be true. And if this formula A begins with a diamond or has the form diamond B, then one first builds the canonical tree for B and then adds one more extra root for this tree below the root of B, and then that will be the canonical tree. So that's a very natural concept here. Then we have this fact one, which states that a sequent A implies B is provable in the system K plus, even only if the formula B is true at the root of this canonical tree for A. So we first build the Kripke model for A, and then check whether the formula B is true there or not. Notice that this criterion is much simpler than the corresponding criterion for the usual model logic K, because there one would need to quantify over a certain set of finite models, which is not explicitly specified here by the formula A as here. So in fact, since it is easy to build, so tree of A is essentially the same thing as A. Computationally, you can easily construct T of A knowing A, and then checking whether a given formula B is true in a given Kripke model is also a polytime decidable procedure. So therefore, this criterion, this fact one, gives you a polytime decision procedure for the logic. Another useful fact mentioned here is that there's a combinatorial criterion how to check that the formula B is true in the root of the Kripke model M. Well, in fact, it amounts to the same thing as finding a root-preserving homomorphism of this T of B into M. So kind of simulation of the model M by B, of T of B by M. Okay, so that's it. Now, what about the other standard model logics? So we call a normal strictly positive logic a set of sequence closed under the rules of plus and the substitution rule. So this is kind of analog of the notion of normal model logic, but in this strictly positive context. And what can we say about, of course, if one takes a normal model logic, then it's strictly positive fragment, namely the set of all implications, strictly positive implications provable in that logic will be normal. So it will be exactly a normal strictly positive logic. The other direction is not necessarily true. We will come to that in a moment. But in the easy direction, so if one has standard model logic axioms. Some of them are already strictly positive, have strictly positive form, like the axiom of transitivity 4 or the axiom T. So these are in itself strictly positive implications. So for them, it's rather clear that adding these principles to K plus gives you the axiomatization of the corresponding fragment. For S5, one would need slightly better idea. So the standard axiom for S5 like negative introspection is not in its form strictly positive. However, S5 allows for an alternative axiomatization, namely this formula 5 written here is would give you an axiomatization of S5 when added to the logic K4 or S4. Then it also gives you a strictly positive axiomatization of the strictly positive fragment of S5. So all these systems are nicely axiomatizable, polytime decidable, so they're well behaved. With Gödel-Loeb logic, the situation is not as simple. However, the answer is simple but somewhat surprising. Namely, the Loeb's axiom does not have a strictly positive counterpart. As it turns out, there is this result proved by Evgeny Dashkov in 2012, which started our interest in this logic. So it was the first paper published on this subject on the provability logic, let's say, point of view. Strictly positive fragment of Gödel-Loeb logic coincides with the strictly positive fragment of the logic K4. So it is axiomatized by the logic K plus and this principle 4 mentioned here. So it's in a sense strange, but understandable. So Loeb is very much non-positive principle, so to say, and there is nothing which remains of it over K4. There are many interesting cases for which it took some time and effort to understand how the strictly positive fragment would look like. One such case is the familiar modal logic of linear transitive irreflexive Kripke frames. So this also known as GL.3. The standard axiomatization of that modal logic involves this axiom, which looks like a disjunction of two such implications under the logic of linear Kripke frames. Of course, it's not strictly positive axiom, so it's a question: what would be the strictly positive fragment of that logic? And that problem was considered by my student Misha Svetlusky. It took him a couple of years to solve this question completely, but eventually the answer turned out to be very nice and clear. As it happens, this axiom can be replaced by another principle, denoted star here. As you see, it also involves more variables than the original principle, 3 variables now. The answer is that indeed this principle star is strictly positive, and it gives you a precise axiomatization of the strictly positive fragment of GL.3 as well as of K4.3. So that's complete answer to this question. And the logic is also polytime decided, so contrast to the original system GL.3. So, of course, in general, strictly positive logics need not be polytime decidable at all. So general principles tell us that there are, even in the class of strictly positive normal logics, there are undecidable logics. And it's in fact quite easy and natural to construct one. In fact, one can interpret any semi-two-way system or one-sided two-way system as a particular strictly positive logic. Namely, consider a finite alphabet sigma and consider a word A in that alphabet sigma. Then one can, with sigma, we can associate a modal language with modalities labeled by letters of this alphabet, like diamond A1, diamond A2, etc. So then every word A can be naturally interpreted as, or translated into the following particular modal formula consisting of a sequence of diamonds over some fixed variable P. And then, having this translation in mind, one can, to a given take an undecidable semi-two-way system with undecidable derivability problem, and then translate each of the rewrite rules into the corresponding strictly positive implication of the form A star implies B star. And then one can prove a sufficiently simple syntactic theorem that in fact a word A can be written into a word B in a given rewriting system, if and only if the corresponding translation of A implies the translation of B in the corresponding strictly positive logic. So this is a reduction of the decision problem of undecidable decision problem to a problem of derivability in the logic LR. So there are plenty undecidable strictly positive normal logics. Nothing surprising in that. This was basically also known in the time of a very long time ago in description logic community who studied this fragment of modern logic language. Another interesting problem, which of a general kind, which is still not completely resolved, is the problem of modal companions of strictly positive logic. So what is a modal companion? A normal modal logic L, whose strictly positive fragment is a strictly positive logic P, is called a modal companion of P. So as I mentioned, to every modal logic, one can consider its set of strictly positive strictly positive implications provable in that logic as its strictly positive fragment. But in principle, not every strictly positive normal logic can be considered as a fragment of some standard modal logic. So the world of strictly positive logics is wider than the world of normal modal logic. But what is the exact relationship? There are some interesting facts. Fact one is that there is this criterion that indeed strictly positive logic P has a modal companion, even only if that logic P is Kripke complete. So and this is even only if statement. So those strictly positive logics which are complete with respect to their Kripke, a class of Kripke frames, they do have modal companions, but and only such logics. This is a consequence of several results. One of them is Salquist's theorem in modal logic, which plays a role here. Item 2 here is a relatively recent result by Kikic, Kurosh, Walter, and Zakharyashev. That in fact, given a finitely axiomatizable strictly positive logic, you cannot determine computationally whether it is cryptically complete. Therefore, it's undecidable whether a given strictly positive logic has a model companion. There is this nice criterion, but it does not give you a decision for T. And then there is this series of questions concerning the structure of model companions of strictly positive logics. For example, one can remark based on choice, axiom of choice, or Thorne's lemma, if you like, that among all the, if a model companion for a given strictly positive logics exists, then there are always some maximal model companions. Simply the chain, extending chain of model companions gives you again a model companion. So there are always maximal model companions. However, in no particular, there are no known concrete cases where we would say that, okay, there is a logic, and we don't have a description of any of its model companions. We know that there exists, there must be maximal, but we don't know any maximal model companion. One notable case is the logic K4 plus, already mentioned before. We know, for example, that the logic K4, so it's a fragment of model logic K4, so K4 is a model companion of that logic. We also know by Dashkov that the Gödel logic is a model companion of that strictly positive logic K4 plus. However, recently Svetlovsky showed that Gödel logic is not a maximal model companion. For some time it was an open question, which I started in one of my papers, whether Gödel logic is in fact a maximal model companion, but the answer turns out to be no, it is not maximal. Svetlovsky constructed several logics above Gödel that which are still model companions of K4 plus. However, this problem has not been fully resolved. So in particular, we don't know as yet whether a maximal model companion for K4 plus is unique or not. So there are more than one or just one. So all natural questions related to this correspondence between model logics and strictly positive logics are still not resolved. Okay. This is goes somewhat parallel to the situation where we consider intuitionistic logics and translation of intuitionistic logics into model logics. There we have Bloch-Esakya theorem, which shows that there is a very nice correspondence between maximal model companions of intuitionistic, of super intuitionistic logics, and up to the isomorphism of corresponding lattices. But here we really don't understand the situation, and of course we suspect that it might be worse than in the case of these well-known results. Okay. So next we come to the next part of my talk. So I'm going to talk about probability logic. I see that I must increase my tempo somewhat. Okay, so here we come to the uses of strictly positive language in probability logic. So in standard probability logic, propositional variables are Propositional variables denote arithmetical sentences, and diamond denotes the function which maps an arithmetical formula A to the formula expressing consistency of A. Strictly positive language, of course, admits exactly the same interpretation. However, since the language is weaker, it is more flexible and admits other interesting interpretations from proof theoretical point of view. And repeatedly, these logics appeared in contexts where propositional variables may now denote not necessarily finitely axiomatized theories, sets of arithmetical sentences rather than single sentences. And diamonds may now denote more or less any monotone operator acting on arithmetical theories rather than just on sentences. And many such operators are actually known in proof theory. They have been studied and have their own interesting meaning. Many of them are so-called reflection principles. Okay, now a few more details here. So we will consider a Gödelian theory, recursively enumerable extension of some minimal theory of arithmetic, like elementary arithmetic, together with a formula, a sigma-1 formula defining provability in T. So that we will call Gödelian theory. So it's not only the theory itself, but also the predicate, the probability predicate for it. Then having fixed this notion on such Gödelian theories, we can introduce a pre-order, natural pre-order, S is less than or equal T if T is included in S, provably in our basic arithmetic EA. Instead of EA, it can be any fixed fragment of arithmetic you like, but for me it's EA. So the difference with, let's say, with this kind of more usual set theoretic approach is that there one would simply define this order as inclusion, or theorems of T are included in theorems of S. Whereas here our definition of order is intentional. We define order as provable inclusion. This is, of course, only possible when we beforehand fixed these arithmetical formulas defining the probability predicates. And then one can factor, so this is a pre-order, one can factor out by the equivalence relation, and one obtains, in fact, a lattice, but we are interested now in its lower semi-lattice structure. The lower bound here corresponds informally to the union of two theories, and formally one should, of course, consider the probability predicate naturally defining this union. Top element in this lattice is the weakest theory here, namely EA. Now, on this semi-lattice of Gödelian theories, we may consider various operators. For example, reflection principles. Reflection principle of T is the sentence expressing that every sigma n sentence provable in T is true. So for every n, there is this corresponding operator Rn of T. And R0 corresponds to consistency assertion. And thus we are arriving at the structure of this semi-lattice with operators. Sort of all Gödelian theories extending EA, semi-lattice structure, and a family, in fact, infinite family of reflection operators. All this is correctly defined. And then the question is, what are the identities of this structure? And the answer to that has been known for some time, but explicitly axiomatized in the work by myself and Dashkov, or Dashkov and myself. So here is the axiomatization of that logic. As you see, it is it consists of the axioms of K4 plus, strictly positive axioms of K4 for each modality, and then the principles mixing the two together. So this system is called RC for reflection calculus. Here is some example of a formal derivation in this calculus, how one can infer something in this weak formalism. And of course, whatever we infer is arithmetically sound, so that will be a valid identity of that semi-lattice. The proof showed the following three results. Firstly, that the system RC is a model, in the terminology of the previous slide, the polymodal probability logic defined by Japaridze, GLP, is a model companion of that system RC. So RC is a strictly positive fragment of GLP. However, unlike GLP itself, RC is polytime decidable as well. So it's a nice computation, and it enjoys a finite model property. So it is complete with respect to a finite class of Kripke models, or class of finite Kripke models. Japaridze proved a hard arithmetical completeness theorem for GLP, and the consequence of that result we get in the previous theorem of Dashkov, we get this corollary that in fact the system RC is arithmetically complete as well. But this is essentially Japaridze's theorem in this context. What is also interesting about that calculus that it gives rise to an ordinal notation system up to an ordinal epsilon naught in a very natural way. Namely, if one considers the variable-free formulas, their modulo equivalence in the system RC, then it turns out that the ordering relation where A is declared to be less than B if B proves consistency of A, then this order will be in fact a well ordering isomorphic to epsilon naught. So that theorem holds, and that theorem in turn was the basis of a consistency proof for piano arithmetic based on these methods, which you can, which I gave in my papers. So that's the system RC. However, arithmetically interesting strictly positive operators do not. So there are other arithmetically interesting strictly positive operators. One obvious proposition would be to consider the full uniform reflection schema for S. So as we know, full uniform reflection schema for S is just the union. You can consider it just the union of the principles Rn of S for each n. Now, that schema has no counterpart in the standard probability logic because it is not finitely axiomatizable unless, unlike the individual Rn's, this whole together does not define an operator on the Lindenbaum algebra of your arithmetical theory. However, it is a legal operator on our lattice of theories. In fact, one can add this operator to the language, sort of diamond number omega, and find the full axiomatization. So here it is. The logic is in fact the logic RC again for all alpha now smaller or equal omega, together with an additional principle. Diamond omega A implies A. So the principle from the modal logic perspective looks very strange because it says exactly as the axiom P implies box P. This is a well-known forbidden axiom in probability logic because in that form it says that your probability is complete, which is never the case. However, here this principle is not only consistent, but it is, as you see, even valid in this very natural interpretation. And one can show that this, firstly, that an arithmetical completeness result for this calculus RC omega. Whereas the fact that this thing has no counterpart in standard model logic, in fact, tells you that the system RC omega has no model companion. So that system is really falling outside the class of strictly positive logics, which are fragments of the standard model logics. However, this system RC omega is still reasonably nice. It is complete with respect to a suitable class of finite Kripke models and is polytime decidable. So here I stress the word models rather than frames. If it were complete with respect to frames, it would be by the previous general facts. It would be Kripke complete, therefore would have a model companion, but it does not. So only Kripke models can be used here for this result. Other cases, I wonder how much time I am allowed to overuse. May I ask the chairman?
Yeah, I'm here. Well, look, we started, let's say 10 minutes late. But, you're officially given 50 minutes.
Okay.
So then I can wrap up with a couple of minutes. It'll be this will
exactly. I'll try to wrap up at this stage. So here are a few other interesting operators, proof theoretically interesting operators that can be studied from strictly positive point of view, strictly positive logic. Transfinitely iterated consistency. So when you iterate consistency operator infinitely many times, in particular, I would rather say alpha times, where alpha is a limit order. And then this theory corresponding to this iteration is an infinitely axiomatized theory. So again, in standard model logic, it's not representable as an operator. In strictly positive, it's okay. Local reflection. Full local reflection is not a finitely axiomatized schema. So, but it is a legal operator to be considered on strictly positive contexts. Number 4, partial conservativity. That's an interesting case where you are given a system, a theory S, and you associate with it the set of all pi n plus 1 formulas provable in S, or the theory axiomatized over EA by pi n plus 1 consequences of S. So what we would naturally usually denote as pi n plus 1 fragment of S. Even if S was a single sentence or a finitely axiomatized theory, this theory need not be finitely axiomatized. For example, I sigma 1 is finite, primitive recursive arithmetic, which is its pi 2 fragment, is not finitely axiomatized. So this acts as again as an operator on the lattice of Gödelian theories and can be considered as strictly leads to some strictly positive logic. Albert Wisser, in connection with interpretability, considered this operator, which is denoted mo by him, and again we consider this a set of consistency assertions for all sentences phi provable in a given system S. Again, this is not a finitely axiomatized set of sentences, but yields an operator. Certain things are known about this. They all yield different logics. For transfinitely iterated consistency, the logic is, I would say, known. Right now, one of my students is working on this. However, in other cases, there are some conjectural axiomatization, but no arithmetical completeness result. So the problem which was left open after my study concerned this pi n operators. It yields this rather interesting system, which I denoted RC number. Don't read these axioms. They are natural and somewhat similar to and based on the system RC that we have so far. So I conjecture that this is a arithmetically complete axiomatization of that probability logic. However, the result is still open. We have a certain characterization of the variable free fragment of this logic, which is in fact quite an interesting one, but arithmetical completeness is still an open problem. So I would like to finish by showing some of the recent papers in that direction, which I published with my students. Thank you very much.
Well, thank you. And I know that you gave this talk under different and difficult circumstances. Yeah, and so thank you. Double thanks for that. Yes. The questions. I think we have time for one short question. Yes. Lev knows I always have one, but
I just sent the remark around, so I will not ask question, but I'll just send a short remark.
Arnie, you want to ask something? Yes. Well, just
remarks are also welcome. Remarks are also welcome.
I just sent it.
Yep.
Just a small question. Why the diamond is used in the definition of positivity and not, say, the box? What's the difference?
Good question. So theoretically, we could easily switch to the dual format where we have disjunctions and boxes rather than conjunctions and diamonds. So reverse all arrows and you get this. Important thing here is that we have, I think what gives this language its expressivity is the combination of diamond, which is kind of existential in terms of Kripke semantics, and conjunction, which is kind of universal. Or alternatively, disjunction, which is kind of existential, and box, which is kind of universal. So that's so there should be opposite kind of polarities of this operation. Why I prefer diamonds here is because in the standard arithmetical interpretations, I want to interpret these modalities as the reflection principles, which are analogs of consistency rather than of probability. So that's also our arithmetical elements of our semi-lattice are theories, right? So sets of arithmetical sentences theories. And if we were to switch to the opposite, to the boxes and disjunctions, we perhaps should then consider something like co-theories rather than theories. So somewhat less natural proof theoretically. So proof theoretically, it's natural to deal with this lattice and then diamonds appear.
All right, I suggest to thank the speaker again, and we'll do it this way. Yes. And the next talk will be five minutes from now, which is 10 minutes after. Please enjoy the break, the shorter way. Lev, спасибо. Thank you. Вы герой.
Ну, все-таки не настолько.